Good morning students. In the previous class we have studied about how to use the operation amplifier for voltage regulation. So, you can see this is the circuit that we have used in the previous class, that is we have the transformer is a step down transformer, and then we had used 18 volt secondary winding, and then we had rectified that AC voltage, and we got the DC here. Across this capacitor you get a DC voltage, that is 18 volt into 1.414 is the DC voltage that you will get here, and then this is the series pass transistor, and then this is the error amplifier. So, this is the output voltage. So, output voltage is divided using these two resistors. So, you get the 15 volt is there, and part of the 15 volt appears here, and this is the reference voltage, and this reference voltage is compared with this output voltage. So, you get some output voltage, that output voltage appears here, and then 0.6 less appears at the emitter and another 0.6 less appears here. Now, this is how the circuit is working. Now, if you see if it is 15 volt, then if this is 5 volt, you will obviously see this comes to close to 5 volt, because the difference between these two, this voltage and this voltage, is amplified by the open loop gain of the operation amplifier and put it here. So, essentially if this voltage is 5, this will come very close to 5, and then that voltage is put here, and if this is 15, I know that this will be 15.6, and this will be if this is 15, and then you will get at this point 15.6 and 16.2, and this is almost 16.2, and then 16.2 divided by the open loop gain is the difference that you will get. So, essentially this is how the voltage regulator is working. So, essentially if this voltage goes up, then this will go up, and the difference between these two comes down, and that makes output reduce, and that reduces this also. Suppose if this goes lower, then the difference between these two increases and the output increases, and again that pushes the output to go high. So, eventually this settles at close to 15 volt. So, this is how the voltage regulator is working, and we had discussed this in the previous class, and I also explained that how to select this resistance value, and then how to select this secondary rating for the transformer, that was discussed. I think that you can see in the so, I had shown you by considering this how much voltage that it is coming here, and then I also shown you that these diodes are not conducting throughout the off cycle, they conduct only during this time. There is a fraction of off cycle only the diodes are conducting. So, the that means the current drawn by the current through the diode during this time will be obviously much more than the load current that is flowing through this. Roughly it is about 3 times, and I also told you that as long as transformer is there for a particular transformer, if you increase the capacitor value, it is not that conduction angle going to decrease. This is because this has an equivalent resistance, and that at anyway charge of the capacitor. So, in practice you find that for quite a large value of capacitor value, the conduction angle remains almost same. For example, if you put very large value 1 farad capacitor, it does not mean the conduction angle will be very small. So, in a practical world, that you will find this conduction angle is about 3 millisecond. For 3 millisecond only it conducts, remaining 7 millisecond of the off cycle the diode is not conducting. And then I also shown you how the ripple is coming, how to select the value of the capacitor and so on in the previous class. Then I had shown you how to compute the secondary voltage. For example, what is required is here for primary 0 to 30 volt, secondary you need 0 to 18 volt. So, I also shown you that because the conduction, if the conduction angle is small, for example, for 1 ampere current, if the conduction is continuous, you will have 1 watt loss in the transformer. Here we have taken 1 ohm secondary, the equivalent resistance of the transformer, and for 1 ampere the loss will be 1 watt. but if I take 3 ampere for 1/3 of conduction time, that is say 3 millisecond is the conduction time, in that case the total loss will be 3 square into R by 3, that is for the same transformer you will have 3 watt loss. That means if I draw the power continuously, the heating is less, but if I draw the same power but very short time with high current, then the heating is more. This is what really happens in the transformer actually. So, when you are using a linear supply, it is obvious that we have to go for much higher capacity transformer than normally what is if I use only resistive load right at the secondary. So, now we will discuss the new topic, that is namely how to design the transformer, because we had given the transformer rating, that is I need 0 to 18 volt, and then I need if it is 1 ampere output, I had shown you I need 1.8 ampere rating to be given to compensate the excess loss that is coming because of the 3 millisecond conduction angle conduction time. So, to compensate that excess loss, we increase the transformer winding and transformer rating so that the heating is normal. Now, it is also important in analog circuit one should learn how to design the transformer, because we will be using transformer at very many places, and then also you will be using inductor. So, it is very much essential to learn about transformer. So, one need not too much worried about so many parameters that comes in for designing a transformer. In fact, transformer can be designed very easily, there is no need of any computer or calculator for that. Now, if you see the generally how the transformer looks like, we have the so called core, if you see the core, this we call E core, we will have a transformer looks like this core. Actually, you have a core, you have this one, then we will have a bobbin here, and in fact we will wind the wires in fact here. This is how the wire is wound, and then to close the magnetic path you have I. So, if I put a AC here, for example, if AC is applied here, then the magnetic field actually completes the path, it comes like this, then other half actually goes like this, and then it goes through this and then completes the path like this, and this half actually comes like this and completes the path. So, if you see a general structure of the transformer, this is what happens. So, we will wind here, and then the magnetic field actually goes like this, and other half it goes like this. Now, when you are winding a transformer, then obviously two questions will come in, namely how many turns I have to put, then what is the thickness of the wire that I have to use. These are the two things one have to decide in the transformer design, because if you see our regular power transformers, the structure of EI core is a standard one, and then this is actually the material also. There are 3 different types of materials available. The core material, say for example, you have one CRGO is there, the second type is a CRNGO type core is there, then third type is called dynamo grade. So, we have 3 types of cores are available in the commercial world, that is this is cold rolled grain oriented, CRGO means cold rolled, this is cold rolled grain oriented. This is cold rolled non grain oriented. This is there is no cold rolling, normal silica steel actually core. Now, this is actually superior quality, the core loss is less, and then you have a little more core loss, and this has much higher core loss. So, if you take these 3 grades of cores are available. So, any of them can be used, only the heating will be slightly different. Right now, let us take for example, CRGO core we take, and then if I put the correct number of turns and the thickness of the wire correct, then it acts as a transformer. But if you look at the core in 3 dimension, then this looks like this, I will normally this is 1, and then we stack them, we will put the many E's one after another is put, and then you get a 3 dimensional view of that you will get. And normally the transformer is made such a way that there is no air gap, and filling this here in the figure air gap had come, but in actual case there is a very small air gap comes, it is stacked such a way that this and this perfectly joined. Now, how many number of turns I have to put, that is the main question. So, the question is how many number of turns. That is the question. Now, if I apply a voltage, if I have a coil, if I apply a voltage to that, then there is a flow of current through the coil, and that actually determined by what is the inductance of this coil. So, if I have inductance L, then I know that the current through that is nothing but V by J omega, because J L omega is the impedance and this F is the frequency, then 2 pi f comes as omega. So, the current flowing through this is given by this. That means, if L is more, obviously small current will be flowing. Then there will be a current flowing through this that produces a magnetic field. That means, if I connect this, the current is flowing through this, that produces a magnetic field, and that magnetic field goes through this, and in fact it is mu r times it is multiplied, and you will have the magnetic field. So, if I put, for example, very low L, that is a less number of turns, and then you will get very low value of L, then you will have too much magnetic field that is generated here, because there will be too much current, and then you will find that too much magnetic field is flowing through that. This core has one problem, then sense that if the magnetic field, if you increase the current here, then the magnetic field will increase. But then if you continuously increase the current, after some value the magnetic field will not increase. The core cannot take more than particular amount of flux. That is, for example, if I take the CRGA core, they will say it can accept only flux density of 1 Tesla. So, we call this a saturation flux density. What is the saturation level? So, saturation level is 1 Tesla, that is the B should be less than 1 Tesla, flux density B should be less than is 1 Tesla. So, if the current is large, then the magnetic field will not increase after 1 Tesla. So, that we call saturation saturation of the core, and we should never allow the core to saturate, because if you allow the core to saturate, the voltage may be changing, but then the magnetic flux in the core will not change. If there is no changing magnetic flux, then to get a secondary voltage, we will find in this the secondary here, and we try to get the voltage here. If there is no changing magnetic field, then no induced voltage will come. And this, and also if there is no changing flux here, this coil itself will have no self induced voltage will not come in this coil, and that will make large current to flow even in the primary, and that will actually make the that large current flowing through that will short the voltage source itself. So, we should never allow the core to saturate, and if once core saturate, then the voltage source will be short circuited and large current will flow through that, and in fact the coil burns off, and you will also get no induced voltage in the secondary. So, it is very important that I should select the number of turns such that I will get the flux density which is less than saturated flux. And if I exactly design, for example, if the core can take 1 Tesla maximum, the saturation flux density level is 1 Tesla, then it is good if I design such a way that maximum flux that I will get in the core is 1 Tesla. That means, I will be using the core very effectively, and that is the best way to design the transformer. So, for example, if I fix L, and then look at then I will go back and calculate whether core is saturating or not. That is a round off way of doing, and then it is not it is also very difficult to get to arrive at a correct number of turns, and then also we have to again check whether flux is saturating. If it is not saturating, again you have to come back and design, change the L. So instead of doing that way, so the basically what is done in the transformer design is, I will find the number of turns, I will put the number of turns such that if I connect the applied voltage, say in this case 230 volt I am going to connect in the primary. If I connect 230 volt, then assume there is whether load is there or not in the secondary, I will first make sure that the flux generated by this coil in the core is exactly 1 Tesla, that is the saturation level of the core. So, that is the basis of designing the transformer. You should not fix L and design the value of N. So, the basic concept is fix B, that is equal to 1 Tesla. That is select a number of select the required number of turns such that when it is connected to 230 volt, for example, it produces 1 Tesla field on the core. So, that is the basic idea of designing the transformer. That means I have to select N so that it produces 1 Tesla. Now, what is the formula that we use? We know that this classic V, so for example, V n omega cos theta, if I take so, for example, the basic formula is B A n omega cos theta is equal to V. The induced voltage in any coil is given by this formula. Now, at the maximum, then we can take cos theta as 1. So, I can remove this term. So, this is the basic relation governing the voltage induced. That is, if I have a coil of n number of turns, then if I apply a frequency of omega and then of frequency say 230 volt, then what is the B that is generated here, that is given by this. For example, in this case I want 1 Tesla. So, B is taken as 1, and the area of the core, that depends on the core size, I will show you that. Then this is the n number of turns I have to put. In this case 2 pi omega is 2 pi f, which is 50 hertz, and applied voltage is 230 here. So, I am applying 230 volt a 50 hertz field, then I want 1 Tesla B to be generated. So, now I have left with two quantities A and N, that is N is the number of turns that I have to put, and A is the area of the core. Now, what is the area of the core? Now, area of the core, if you see carefully, that our actual core, what we used, E core, you know, we are winding here that core. So, this is the area of the core. So, here only the magnetic field is generated, and this is the area of the core that that actually fixed in this. So, we know that if I know the area of the core, then I know all the parameters. So, N can be determined. So, that means the number of turns that is required is actually you have this divided by that area into 2 pi into 50, and that field B is 1 Tesla. So, one can, depending upon the area of the core, you have to select the number of turns that is required. That means, if I put that many number of turns here, and if I give 230 volt 50 hertz, then I am sure that 1 Tesla field only will be set up in this core. That is, we had seen our earlier this thing, that the magnetic field goes like this, and you will find that here 1 Tesla field, that the flux density will be only 1 Tesla, here also 1 Tesla, and the core will not get saturated, and we are also utilizing the core fully, because if I do not set up 1 Tesla field, that I am not utilizing the core fully. So, this is the first principle that we have to look into that in designing the transformer. Then once number of turns are decided, then I should see what is the thickness of the wire that I have to use. So, the next question is that what is the thickness of the wire to be used. So, now to go into that, we should see little about the secondary circuit, because this is the primary and you have the core and then you have the secondary voltage. Assume it is a 1:1 transformer, you have n number of turns here, I have put n number of turns. So, n number of turns is decided, as I said, using this formula. So, you know you are selected the n number of turns. Suppose if the sender is 1:1, then here also you will have put n number of turns. Suppose if I connect the load, then what happens? You can, because now I applied a voltage here, that actually produce a magnetic field, that is a current, and that produces a magnetic field. That magnetic field is a changing magnetic field. So, that induces the voltage here. Now, the induced voltage, because it is 1:1 transformer. So, if it is 230 volt, I know that I will get again 230 volt here. Now, for example, if I put here 230 ohms, then I will have 1 ampere current here. Now, secondary current is known. The next question is, what is the primary current? Because depending upon the current only, we have to select the thickness of the wire. That is what we are seeing now. Now, one important thing in transformer is, for example, if there is no load in the secondary, for example, I will put nothing is there, you know, I keep it open here, you know, the secondary is open, there is no current here, then only primary is connected. Now, there will be a current. What is that current? That current is the one which produces the magnetic field in the core. Now, why that current is coming? Because if I take, there are two ways of looking at it. If I have n number of turns, then I know the inductance of the primary is given by this. That is, we know the A is the area of the core, because I had shown you in the thing what is the area actually. So, you have the, this is the area of the core. Now, here the L, the path length L is actually this, you know, you start here, go like this and enter, that is the L. So, you know, the two rounds, so one of them to be taken. So, that is the L, that is where the, that is the path length of the magnetic field. So, that is the value L, and mu r invariably for this core is around 3000. For the CRNGO core, if you are in CRGO core, if you take, this is actually coming as 3000. The mu naught is known, that is 4 pi in 10 power minus 7 Henry per meter. So, we know already we have selected N and we know L, all the quantities are known. So, one can we can find out what is L. So, if L is known, then primary current will be, the primary current can be determined. So, primary current actually is given by V by L omega. So, since L is known and the frequency is known, one can find the primary current. So, if secondary is open, there will be a current flowing through this, that we call as a magnetizing current, and that current is given by V by L omega. This current is invariably very small, that is the one which produces 1 Tesla flux in this. Now, you may be wondering, why only that much current is flowing. If I have connect an inductor, why only small current? For example, if the inductor is few Henry in a normal transformer, is 230 volt AC, fine, only few milliampere current is going through this. This is happening because of the self induction, because when the current is flowing through this, and then this is AC current. So, this current flowing through this AC voltage, so current flowing through this, the current flowing through this is also AC. So, the magnetic field set up by this is AC, that changing magnetic field will induce a voltage here as well as induce a voltage in the ear itself. So, this is a self induced voltage, this is actually mutually induced voltage. So, when magnetic field changes, it induces a voltage here and as well as here, but this induced voltage will always equal to the applied voltage. and this induced voltage always opposite that of applied voltage, and always it will be equal to the applied voltage, and this is the one which opposes this. That is the why the current flowing through the primary is very small when there is no load in the secondary. Of course, when you load the secondary, for example, if I connect a load here, resistance R, then there will be a current here. This current will produce a magnetic field in the secondary. Now, the secondary magnetic field is opposite that of primary magnetic field. So, what is really happening is, if I connect a load in the secondary, then there is a current in the there is a current in the secondary coil. So, this current in this produce a magnetic field, since this and this are coupled. So, if more current flows here, then you get more magnetic field generated because of this, and magnetic field generated by this, and magnetic field generated by this due to this, this in the primary you have already some magnetic field generated. Now, because of secondary current, there is a magnetic field generated by this, and this magnetic field is opposite of this. So, this magnetic field cancels off the primary magnetic field, and net result is, since the reduced magnetic field, then again more current trying to flow through this, and the more current flowing through that produces again more induced voltage, and which always trying to match with this. So, net result is, when I load this, then you will have magnetic field cancellation, and then to get back to the original field, more current now goes through that. So, other way around, if I load here more, then I will find more current is flowing in the primary also. So, primary current consists of two currents. One is the magnetizing current, that is when there is no load here, what is the current that is flowing. Then second one is, if I put a load, then the load current also reflected into the primary. So, you have two components, one is the magnetizing current, other one is the secondary reflected current. So, this should be understood clearly, because yeah. So, the 2 points, that is primary current consists of 2 parts. One is magnetizing current, that is nothing but V by L omega. In fact, J L omega indicating that the current is 90 degree phase shifted with respect to the applied voltage, and the second component is reflected secondary current. So, there are two components. Now, the reflected secondary current, for example, if it is 1:1 for 1:1 transformer, that is secondary or primary or 1:1, then secondary reflected current equal to the reflected current equal to secondary current. For example, if it is the secondary current is a 1 ampere, then the primary reflected primary current also 1 ampere. So, you will have this 1 ampere, that is if the secondary current is 1 ampere, then the primary current consists of the reflected current of 1 ampere plus the magnetizing current, which is normally very small, maybe around 0.1 ampere. So, the total current will be secondary current plus this one. Normally, we can neglect this current in considering the transformer, because this will be invariably very small. So, in this case, I had to design, in this transformer, I have to see that the primary turns are taking at least 1 ampere plus this 0.1 ampere, neglecting this 0.1, the primary wires would be able to carry 1 ampere current. Of course, the secondary wire also had to carry 1 ampere, because it is 1:1 transformer. So, I had to select the current, the thickness of the wire corresponding to 1 ampere. So, the normally to avoid overheating, we take per 1 mm square 3 ampere current we take. That is, if I have a wire, we are winding the wire, then we have the cross section of the wire. If I take, if this pi r squared is 1 mm square, then I can pass 3 ampere current. That means for 1 ampere I need 0.3 mm square cross section area. So, that is the area of the wire that I need. So, I have to select the thickness of the wire such that the cross section area is 0.3 mm square, then it can carry 1 ampere current and transformer will not get heated up too much. Now, this 0.3 ampere per mm square come from practical value, because we know that the transformer can go only above certain temperature. Based on that, we had fixed this. This also can be seen in detail if possible at a later time. So, so this is how the thickness of the wire and the number of turns to be selected. So, in summary, if we see that if I am designing a transformer, then I will select the primary number of turns n, and then I will select the secondary number of turns. Of course, once primary is selected, secondary automatically decided, because if this is 1:1, for example, if I ended up with 1000 turns here, and if I want 1:1, then I put here also 1000 turns. And if I want step down, say off here 230 volt, I want 115 volt, then 1000 turns here arrived at, that n arrived at using this formula, BA 1 omega is equal to 230. Using this we arrived at n for a given A, and then if a step down of off required, then I will reduce this to 500 turns. Then if we are 230, I will get if I put 500 turns here, then if I put 500 turns, then I will get 115 volt here. So, n number of turns of this is decided, then automatically depending on the requirement of secondary voltage, this turns is decided. Then the thickness of the wire. So, thickness of the wire is decided by taking 3 ampere per mm square. That means, I should estimate what is the primary current, what is the secondary current. If it is, for example, in the previous example we arrived at 1 ampere primary current, then 1 ampere means I need 0.33 mm square of wire to be put. In the secondary also, if it is for example, in even our earlier case we have taken this also 1010. In that case, if 1 ampere load is there, then here also 1 ampere. So, here also need 0.3 mm square. So, that is how the number of turns are selected. Now, one question may arise that if you are arrived at this n number of turns and the thickness, will the core hold that number of that turns, because when you are winding, we are winding the if you see the how the core looks like this. I said we are winding it here. So, this core must be able to take this many number of turns of that much thickness. That one can find, because I know the diameter of the wire. So, I will know how many turns that it can take. For example, if I carefully draw this, you know, you see, for example, if I take the core and draw this, one can easily verify what is the number of turns that it can take. For example, if I am putting 1 turn, then it occupies 1 diameter length. So, if then I can ask how many turns that one layer can take. So, if this length is say 20 mm, then if the dia is 1 mm, then it can take 20 turns in one layer. So, we are winding like this. So, it start 1, then you will be able to put 20 turns, because this length is 20 mm. If this is 20 mm and dia of the wire is 1 mm, then it can take 20 turns. Then the next question is next layer. I will wind the next layer here, the next layer will be wound, then third layer will be wound, then fourth layer will be wound. That means, if I see how many layers it can take. So, if this is each one is 1 mm, then each layer it can take. So, for example, if this is 10 mm, then it can take 10 layers. That means 10 layers, and each layer can take 20 turns. 10 into 20, that means it can take 200 tens of 1 pi is equal to 1 mm. The dia of 1 mm wire, it can handle 200 tens. So, one can always verify whether the given core will take that number of tens or not. Because we know that half the transformer is occupied by the primary, other half we had allotted for secondary, because the total area occupied by the secondary is equal to total area occupied by the primary. So, normally we allot half the area per primary, other half for secondary. So, one can always verify from this whether the transformer can take this number of tens or not. If it is not taking, then we have to go to next higher size. So, once you go to next higher size, the area will change and then tens also will come down, then the area this this distance and this height will be different. Accordingly, you can again verify whether it takes. So, this is easier way of doing this in the academic environment. But then actually in a real world, what they do is they know the core size, and once they know the core size, they know how much wattage it can handle, and according to the wattage they select this. That is what you will see in the textbook and all other design books, and there is no compulsion that one have to follow that route only. It is easier to follow the route that I had shown to you, because you have a core in the academic community in your hand, and then further core you can always find out whether the given wattage can be obtained or not, otherwise you can go to the next core. Or if you want to go academic in the commercial way, then also if you have a different size of core, one can always find out how many tens it can handle and how much power it can handle, because we know that if, for example, in this case it is 200 tens it is handling, and then I know the current rating of how much by taking 3 ampere per mm square, how much current the wire can take. In that case, I know the current rating and then the voltage rating, I can decide how much power the core can take. So, it is only just think about this and apply your mind, and you will immediately see that the transformer can be designed in both ways. So, the way I have discussed shown to you is good for the beginner, and then particularly good in the academic environment. So, follow this, and if you have a if you look at the textbooks or the transformer design books, invariably they follow the reverse of what I have told you, and in fact that not helped, and we found that understanding is more difficult going that textbook route. So, you can kindly follow this route, and then if you want to reverse work and see whether it fits in, but nevertheless both will give you the same result. So, need not worry about that. This is how the transformer to be designed, and I had explained this transformer design at this point of time, because we will be using this at very many places in the analog course, because for example, we will be using LVDT, there we have to wind the coil. We will be using current transformer to sense the current, there we have to wind a coil, and we will be using filters, there we need an inductor, there we will be designing this. So, all along the same formulas will be used, and as an analog circuit designer, in fact as an electronic engineer, it is a must that one should know how to design a transformer, otherwise you will not become a good electronic designer. The reason is that you will be using at very many places, and it will be like your half the hand is cut if you are not knowing how to design the transformer. That is why I had spent this much of time in explaining how to design the transformer. So, once you know how to design the transformer, then of course, you can either design or get it done by giving the spec. Nevertheless, for a regulator to work, we have to fix the transformer first, that you can do it in either way, either you design it or you buy it. Now, if you go back our actual design of regulator, then another issue that we have to see would be how to select the heat sink here, because we have this transistor here, and now this transistor invariably heats up. For example, this heats up, and then once it heats up, the temperature of the junction will go up, and we know that in transistors, if the junction temperature goes more than 150 degree, the transistor goes bad. So, we have to make sure that this transistor works as we like, and because of heating, this transistor will not go bad. And there is another issue in that, if I take this transistor, for example, when I load this, then it heats up. If there is no load, then the very small current is flowing through this and transistor does not heat up, because in a normal case, for example, if the input voltage if the input voltage is here is say 25 volt, the output is 15, then you will have a 10 volt across this, and then if 1 ampere current is flowing through this, then you will have 10 watt of heat dissipation on this transistor. If 10 watt heat is there, then it will be heating up. Of course, if the load current is not 1 ampere, if I increase the resistance, the load current comes down, then the heating comes down. So, depending upon the load, the transistor heats up, but whatever may be the case, I have to make sure that the transistor will not go bad, or the life of the transistor is not getting reduced because of the heating. Now, I introduced the term life of the transistor, because if the heating is more, then the life of the transistor is less. This is because when you assume that this is you are using it for a TV. In the TV, what happens, you will be switching on the TV and watching the program in the morning, then after some time you will switch it off. At that time, this would have heated up, the junction would have gone to some temperature, maybe say 100 degree or 120 degree. Then you switch it off and go back, and at noon time you may switch on the TV again and watch the program. Again the noon time, this again will go back to 120 degree, and then you switch off, then this also comes back after some time to room temperature. The night again you will switch on and see the program, and again this temperature will go high, say 120 degree, and come back to room temperature. So, if you see a TV, typically there will be 3 thermal cycles. The temperature goes up, then comes back, and noon again goes up and comes back, and again in the night goes up and comes back. That means 3 times it is heated and cooled in a day. That means in a year roughly 1000 times it is heated up and cooled. When this transistor is heated up, then inside the connecting wires and then the silicon, everything heated up, and they are all stretched, and when it cools down it comes back. Every time when heating and cooling, there is a thermal fatigue develops inside. Then after several cycles, the wire bonding actually breaks inside. So, how many thermal cycles the transistor can withstand depends upon how much temperature it went and how much it had come back. So, the delta T is very important. So, if it is morning it went to 120 degree and come back to 20 degree, means thermal cycle 100 degree temperature change occurred, and it the bonding wires inside expanded and contracted. So, if it is, for example, if I operate the transistor say at junction temperature 150 degree, so that is what maximum allowed, then you will find the transistor goes bad in about 200 to 300 thermal cycles. Whereas, if I operate the transistor at 100 degree C, that is I limit the junction temperature 100 degree C, then this comes even more than 10,000 thermal cycles. If I operate at 80 degree, it goes even more than 1 lakh thermal cycles. So, it exponentially life increases if I reduce the temperature. So, I should never attempt to operate this at 150 degree. In that case, the life will be less. For example, if you design this transistor such that every time when switch on, the temperature of the junction goes 150 degree, then probably if you are using it in a TV, in 3 months time your TV had to go for servicing because this transistor would have blown up. So, depending because this transistor, the voltage regulator decides decides the life of the equipment very critically. So, one have to think what is the life of the equipment and how much the junction temperature that I have to keep, and then if I had to reduce the junction temperature, what I have to do. For example, if I want to keep it much cooler, then what I do is I have to put it in the heat sink, so that the heat goes out and the junction is kept at much lower temperature. And the heat sink plays a very crucial role in deciding the life of the equipment. For example, if it is a defense equipment where only once it is operated, for example, if it is a missile, then you fire the missile and it goes and gets destroyed once for all. So, the life is only once. So, there I need not design the junction to a much lower temperature, but that will if I have to design for much lower temperature, I know I have to put a heat sink, and the heat sink size is bigger, that means the equipment size will go up. So, depending upon the life that is required for the equipment, I have to decide on the heat sink and then the junction temperature, because the heat sink ultimately decides the junction temperature. This is a very important thing for any circuit designer, particularly the for voltage regulator. This is very important, because the voltage regulator is the critical part of the equipment where most of the heating is taking place, and that decides the life of the equipment, because if the voltage regulator fails, then the whole equipment fails. So, depending upon the junction temperature, I have to decide the heat sink. Assume that I want a life of say 1 lakh thermal cycles, then I want to keep the junction at say 100 degree C. Then assuming that, let us design the heat sink now. So, heat sink design I will look into that little carefully, because heat sink design is very important for analog circuit design, because you have to use the heat sink at very many places. So, first fix the junction temperature. As I explained to you that depending upon the usage and what is the life of the equipment, you have decide, and in this case let us assume let it be 100 degree C. Then the second step is, what is the maximum ambient temperature? What is the maximum ambient temperature, because the equipment have to work in the ambient, and then if I am putting a heat sink, the heat sink basically radiates to the ambient, and depending upon the ambient temperature only you will have the heat sink size. For example, if it is a laboratory equipment, then expect ambient temperature is 0 to 70 degree for lab equipments. Then for industrial grade equipment, it is minus 20 degree C to 80 degree C for industrial grade equipments. Then for mill spec we have minus 40 degree to 105 degree C for mill grade equipment. For military applications we need much higher temperature. So, we have to select which what is the operating ambient temperature. Let us take in this case we are working with the lab grade equipments 0 to 70 degree C. That means my maximum temperature ambient temperature going to be only 70 degree. Now, if I take that is the case, then that means we are now fixed the two things, that is junction temperature supposed to be not more than 100 degree C. Then the second one is ambient, T ambient is actually 70 degree C. So, when the ambient is 70 degree C, the junction temperature should not go more than 100 degree C. Then next thing I should decide what is the power dissipation on the transistor. Power dissipation is voltage across the device, voltage across the series pass transistor into current. So, in this case if the input is 25, my output is 15, 25 minus 15, that is a 10, and if it is 1 ampere current, then it is 10 watts. So, I decide on what is the power dissipation, that is the we have taken as 10 watts. Now, we have to see how the transistor mounted in the real world. So, normally what is done is you have a transistor, and all the power transistors invariably you have a junction here, this is the junction here. this is the case of the transistor. Then, so whatever heat that is dissipated here, the 10 watt is dissipated here, and that has to come to the case. Now, from the case, what normally we do is we will put a mica actually to insulation, to insulate the heat sink, we put mica here, then we will put the heat sink. So, basically what really happens is in the junction heat is developed, from junction the heat comes to the body of the transistor. So, this is the body of the transistor, which is invariably collector in case of power transistor. From the body it goes through, actually there will be a small gap here, there is a small gap here, this is normally filled with heat sink compound. So, this void I just showing here, but it is normally filled with heat sink compound. So, heat has to come from here to here, then here to heat sink, and then heat sink to ambient. So, ambient is sitting at 70 degree C. So, heat dissipation is eventually from the heat sink, but then we know that heat has to come from here to here through these things, and then from here it has to radiate out to the ambient. Where heat has to go means there needs a temperature difference. That means, if this is 70 degree, if the heat has to be radiated by the heat sink will be more than 70 degree. The heat sink then this mica has to be more than heat sink, then the case must be more than the mica, then junction must be more than the case, because the heat is flowing like this. That means, this is higher and the case is little lower, then this is little lower, this is little lower, this is little lower than that. That means, obviously junction will be that is heat sink will be more than 70, and this fellow will be more, say if it is 80 degree, then this will be more than 80, and if this is say 85, then this will be more than 85, and if this is say 90, then this will go more than 90. So, all that we need to do is that we have to make sure the junction is not more than 100 degree C. For that, what is the heat sink size I have to select. Now, if I look at the data sheet, for example, if I take data transistor say 3055, 2N3055 is a high power transistor, general purpose transistor, which is available for the normal use very easily. Now, if I take this, look at the data sheet, he gives one data, that is thermal resistance between thermal resistance from junction to case. He says it is 1.5 degree C per watt. That is what is the thermal resistance junction to case, that is if I dissipate 1 watt of heat in the junction, then that 1 watt has to come here, you will find the case and junction will differ by 1.5 degree, that is the case will be 1.5 degree higher than the junction. So, if it dissipates 10 watts, then the case will be 15 degree higher than the junction. Then similarly, I have to find out what is the thermal resistance of the mica, that is the insulator. So, mica thermal resistance is 0.5 degree C per watt. Then similarly, that means this is 1.5, this is 0.5, that means 2 degree temperature difference will be there between junction and the mica per 1 watt of heat to go. If 10 watt heat had to come, then you will find this and this differ by that is if 10 watt heat is coming, then you will find this and this differing by 20 degree C. Then from here you know that is this and this are at the same contact. So, if I take the for example, if then from here the heat had to go to ambient. Now, if I put a bigger heat sink, then thermal resistance from heat sink to ambient will be smaller. Assume I have put a bigger heat sink, because that from heat sink size you can find out the thermal resistance from the data sheet of the heat sink. Suppose if the thermal resistance of the heat sink is say 0.5 degree C per watt, and this thermal resistance is 0.5 degree. this is 1.5 degree. That means total thermal resistance from here to ambient, if I take 1.5, another 0.5 for mica 2 degree, and then another 0.5 for heat sink, 2.5 degree is the thermal resistance from junction to ambient. That means for 1 watt dissipation of heat here, you need 2.5 degree difference between ambient and the junction. So, if 10 watt is dissipated here, then you will find 25 degree difference between the ambient and the junction. That means, if this ambient is 70 degree, then junction will be 95 degree. So, if here for example, 10 watt dissipation case, this is 0.5 degree, this is 70. So, 10 watt dissipate, this has to go for every 1 watt 0.5 degree. That means, for 10 watt it will be 5 degree higher, that means, this will go to 75 degree. That is, then only 10 watt will go, because this dissipation is 0.5 degrees C per watt. So, to 10 watt to dissipate, you need to have 5 degree higher than the ambient, then this has to be 5 degree, because here again 0.5 degree temperature difference. So, 10 watt is going, so this will go to 80 degree. Then from anyway, these two are actually there is no gap here filled with heat sink compound. So, this is case is at 80 degree. Then junction will be again 10 watt has to come, this is 1.5 degree. So, for 10 watt 15 degree difference is required. So, if this is 80 degree, this fellow will go to 95 degree. So, this is at 95 junction, case is at 80 and mica is at case is at 85, the case is at 80 degree, sorry, because for 10 watt 1.5 degree case is at 80. That is same as mica 80. Then the from mica, then heat has to go to this, and this fellow will be sitting at 75 degree and the ambient is 70 degree. So, we have to decide on the heat sink depending upon the junction level that we need. I will discuss more about this in the next class. So, we had seen in this class the two important things, how to design the transformer and how to design on the heat sink, because unless you design the heat sink correctly, the junction temperature may go high and the life of the equipment may come down. So, we have one or two more issues that we have to discuss about the regulator before going into the other topic. So, thank you.